So in this case of always, never, sometimes, the floor fall, the slam, and the toss were a lot of sometimes. Can somebody give me when it's not? If it's not always, then your answer was it's sometimes. When is that sometimes that it's in free fall, and when is it not in free fall? This is where one of you has to jump in and say. So there were a bunch of you who said sometimes.
Is this for the second one?
Pick one.
For the second one, I said sometimes in free fall, which would be like after it reaches its like maximum height, then it's in free fall.
So you're saying it's only in free fall on the way down and not on the way up. Would that be the same thing for the other two? Like when it's on the way up, it's not in free fall, or when it's on the way down, it is?
Not always. Like for the slam, like when it was on the way down, you were applying that force that the way down is free fall.
Okay.
But then when it you let it go up and then fall into your hand, and before it fell into your hand, it wasn't free fall.
So only that third section, not on the way down, not on the way up. Yes, on the way down. Okay. Anybody else have any different sometimeses? So the correct answer is always for all of them. There's one little minor exception where sometimes would have worked for the floor toss and the slam, and that's that brief moment when it's in contact with the floor, then the floor is putting a force on it. Other than that, now we are going to assume, because I think it was James, said, what about air resistance? So for the most part, we're going to ignore air resistance because over this short distance, it doesn't have any effect. But technically, so we're going to pretend we're in what's called happy physics land, where there is no air resistance. So in happy physics land, this object is always in free fall. Even in the slam, because remember, I said start when it leaves my hand. After it leaves my hand isn't putting any force on it. Even though I threw it to start, once it leaves my hand's not doing anything to it anymore. It's all gravity. So in all of these cases, once it leaves my hand, the only thing that's acting on it is gravity. So it's always in free fall. So a couple things about free fall. One, only force acting is gravity. Okay, so we're going to be in happy physics land, so we're not going to worry about air resistance at this point. So gravity is the only thing acting on it. The object's always accelerating, right? It's changing velocity. Whether it's on its way up or on its way down, the velocity's changing, right? If I throw a ball up in the air, it leaves my hand. As soon as it leaves my hand, it changes velocity. It doesn't shoot up to the top at one velocity and then shoot back down at another. Okay? It's always changing velocity. So it's always being accelerated. That acceleration is constant and negative. Okay? The acceleration is constant and negative. It's so special, it gets its own letter, little g. Okay, little g, we're going to call it the acceleration due to gravity. its value is negative 9.81 meters per second squared. So anytime an object is in free fall, that means it's the only thing acting on it is the force of gravity. It's accelerating at a rate of negative 9.81 meters per second squared. So little g, the acceleration due to gravity, or it's also known as the gravitational field strength, like how strong the gravitational field is that's pulling on the object. Okay, like on the moon, it would be less because the moon has less gravity than the Earth. But the Earth's gravitational field strength near the surface, as you get further away from the surface of the Earth, this value for acceleration due to gravity, the gravitational field strength, does decrease a little bit. We'll talk about that a little later. But the acceleration due to gravity, negative 9.81 meters per second squared. Now, we had 4 formulas from before. 3 of them had a value for acceleration now, right? So, if you don't remember them, first equation was using the average velocity times time. The second equation was the rewriting of the definition. The third one was, oops, I forgot the 1/2. 1/2 AT squared plus BIT. And the last one, EF squared, BI squared plus 2AD. Those 4 equations, in particular, these 3, are going to be exactly the same for an object in free fall. Because an object in free fall has a constant acceleration. And since it has a constant acceleration, we can use these kinematic equations to solve the problems. The only thing you have to do is replace the acceleration with g. So they just become, right? This one just is final velocity equals gt plus vi. Okay, so all you have to do is take the a's out, substitute in g, the acceleration due to gravity. So they're pretty straightforward. Same formulas, just a different idea. So let's take a look at how they work. So, a rock is dropped from the top of a 30-meter cliff. How long will it take to hit the ground? And B, how fast will it be going when it reaches the ground? Okay, so I will, of course, follow the 5-step physics problem-solving system. So I'll start with a beautiful drawing. There's my cliff. There's a person standing on top of the cliff. And here's a rock that they are dropping. So the rock's going to fall, going to hit the ground. I know the cliff is 30 meters high. And that's all I got. That's all the information I have in the problem. So, step 2, list my variables. The variables are the same variables. The I, the F, A, D, T. Okay, same variables. I'm going to start filling in variables. As soon as I look at my picture here, I see when I drop the rock, it's in free fall. So as soon as I recognize free fall, I know that the acceleration is g, which is negative 9.81 meters per second squared. Okay, now I have to fill in some other variables if I need them. Let's see. Initial velocity. Well, if I'm holding a rock at the top of the cliff, when I let it go, the initial velocity is 0. It started in my hand at rest, so when I let it go, I had an initial velocity of 0. Final velocity is what question B is asking me for. Right? How fast is it going when it reaches the ground? That's question B. And question A says, how long will it hit the ground? So this is question A. So I must know the displacement. This is where you got to be careful. The displacement, it starts up at the top and it goes down. It has a negative displacement of 30 meters. The negatives, you got to be very careful about the positives and negatives, your directions in these problems. Right? Its total displacement starts at the top. Even if you called the ground the reference point, it started at positive 30 then and wound up at 0. It has a negative displacement of 30. If you call the top the reference point, it starts at 0, and when it hits the ground, it has a displacement of negative 30. So the displacement's negative 30. All right, so now I'm ready for step 3 for part A, which is choosing an equation. I need to find the time, and I don't have final velocity. So I need the one without final velocity. So if I go back and look at my equations, the one without final velocity is equation number 3. So I'm going to put down E equals 1/2 gt squared plus vit. I'm going to substitute in my values. Negative 30 equals 1/2 times negative 9.81 t squared plus 0 t. So I'm going to solve that. I can do this. It's in my head. Negative 30 equals negative 4.905 t squared. Ooh, I'm going to need a calculator for this one. So t squared equals negative 30 divided by negative 4.905. So the negatives are going to cancel out. And now I need a calculator for the rest of that. Don't worry, I am recording this, so I'll post it when we're done so you can take a look at it. So 30 divided by 4.905 is 6.12. And then I'm going to take the square root of both of those. So square root of 6.12 gives me a time of 2.47 seconds. Okay, 2.47 seconds for that rock to hit the ground. Okay? Part B, which asks, how fast will the rock be going when it hits the ground? Now, you can use this 2.47 that we just found as the time, but I'm going to give you a bit of a caution. If you made a mistake in finding the 2.47 and then use that number to calculate the final velocity, you're going to get the wrong final velocity. So while sometimes you have to, I prefer not to use a calculated value if I don't have to. Sometimes you have to. This time I don't think we do, because I want to find a final velocity without time. So looking back at my equations, that would be equation number 4 has velocity, is the one that doesn't include time. So I can use, Vf squared equals Vi squared plus 2Gd. So Vf squared equals 0 squared plus 2 times negative 9.81 times negative 30. See, if I didn't have that negative 30 in there, I'd be in trouble because I'd get a negative number over here and I can't take the square root of that. So Vf squared equals a little bit less than 300, right? No, a little bit less than 600. So let's see. 2 times 9.81 times 30, 588.6. I'm going to take the square root of both sides. So 24.26. So my answer is 24.26. That is not the correct answer. What? Mr. Spears, you just did all that work and that's not the correct answer? No. Why isn't it the correct answer? Goes back to a question I asked you a couple days ago in question of the day. What's the square root of 25? Positive or negative? Right. So in this case, what direction is the velocity? It's down. We got to remember that this square root can be, and in this case, must be the negative value. Negative 24.26 meters per second. Okay? This equation doesn't know what direction the object's going. It just knows I'm taking a square root. So it's important to remember you got to include that positive or negative, and you have to decide, do I want the positive value or the negative value? And in this case, you want the negative value of the square root. Okay, so that one was pretty quick. Again, I'm recording this, so I'll get it posted, so if you missed it or want to go back over it, you can go over it again. I know I'm going pretty quick, but I want to try and get these done during class, because I got one more I want to go to show you. Okay? The ball is thrown vertically upward with a velocity of 6.2 meters per second. How high does it go? And how long is it in the air? Hand. Crossing the green ball of physics. Coming back down. Okay? Cross it up. Comes back down. It leaves with an initial velocity of 6.2 meters per second. Again, that's all I got from the problem. The rest of the things you have to kind of figure out as you go. So let's start with our list of variables. Again, I know once the ball leaves my hand, it's in free fall. So I know the acceleration is going to be g, or negative 9.81 meters per second squared. And I know it starts with an initial velocity of 6.2 meters per second. That's all I got. Okay, so we have to make a few, not assumptions, but make a few actualizations to realize what's going on in the problem here. So let's talk about part A. How high does it go? So we're talking up here at part A, how high does it go? Or what's its displacement? What also happens to the ball at the top of the toss? What happens to the, I'm going to ask you this question. What happens to the ball at the top of the toss?
Comes back down.
Okay, but at the very top, what happens to it? Yes, it has to stop briefly at the top, right? It's going up. If it's going to switch from going up to coming down, there has to be an instant in there where it comes to a stop. We're going to use that fact and say at the top, the final velocity equals 0. At the top, it stops for that brief moment, so it has a final velocity of 0. So we can use that. And we're just still going to have VI is 6.2 meters per second. We're now going to put in a final velocity of 0 meters per second, an acceleration of negative, we'll make it G, 9.81 meters per second squared, a displacement, and a time. We're looking for how high the displacement, so I need the equation without time again. And if I think about that, that is back to equation number 4. Df squared equals Vi squared plus 2GD. 0 squared equals 6.2 squared plus 2 times negative 9.81 D. Oh, I can't do 6.2 squared in my head. 36, 38 something, right? Let's see. 6.2 squared. 38.44. So I get negative 38.44 equals negative 19.62D. Divide both sides by negative 19.62, and I get D equal to 1.96 meters. So if I toss an object up with an initial velocity of 6.2 meters per second, it's going to go up about 2 meters, 1.96 meters, and it starts to come back down. But I had to use the fact that at the very top, the final velocity becomes 0 just for a brief second. Okay. Part B says, how long is it in the air? How long did it take to go from my hand and come back to my hand? So we want to know how long it took to get back to the hand. So we have to use another implication here. How long in the air? What's true about the displacement when it comes back to my hand? What's the ball's total displacement when it gets back to my hand?
0.
0. Right? So we're going to use that for how long in the air. The displacement is 0 meters. It gets back to where it started. I'm going to have to do a little page extend here. There we go. So DI, 6.2 meters per second. EF, we don't know. G, we know is negative 9.81 meters per second squared. Displacement is going to be 0 meters. And time. That's what we're looking for. So I need the equation without final velocity. I just have to remember them. You will eventually, maybe. D equals 1/2 GT squared plus VIT. 0 equals 1/2 times negative 9.81 T squared plus 6.2 T. Uh-oh. What kind of equation is that? is where somebody goes back into the mathematical history and goes, oh, I know what that is. That's a equation of a parabola. It's a quadratic, right? It's got a second power into it. We learned 4 ways to solve a quadratic equation back in Algebra 1. You can graph it, you can factor it, you can use the quadratic formula, or you can complete the square. I'm sure you remember all 4 of those ways. Right? Graphing, completing the square, quadratic formula, factoring. I'm going to choose to factor this one because that's the fastest, easiest way to do this one. Because I can factor a t out. I got like 2 minutes, so I have to hurry. So this is telling me there are 2 answers to this equation. At the displacement, remember we set the displacement equal to 0. So the displacement is 0 when t is 0. That makes sense. It starts in my hand. So the time is 0 and the displacement is 0. But that's not how long it's in the air. The other thing is t is when this thing is equal to 0. 4.905 t plus 6.2. When that part of the binomial is equal to 0, right? In order to get 0, you got to multiply by 0. So either the first factor 0 or the second factor 0. So we want to figure out when that second factor is 0. So it's going to be negative 6.2 equals negative 4.905 t. .2 divided by 4.905. 1 point something. And we got t is equal to 1.26 seconds. I'm going to stop that recording.